Okay, so we'll start talking about Kalman filter. This is actually stochastic state estimation. We're going to talk about, first of all, the big picture of the Kalman filter, and then we'll go through the first three elements. We'll talk about mainly discrete time Kalman filter. Then next time, we're going to talk about some of the properties, and then we'll go to continuous time Kalman filter. By the way, discrete time Kalman filter was invented by a mathematician and a famous engineer, Rudolf Kalman. He invented discrete time Kalman filter first, and then 1 or 2 years later, he invented continuous time Kalman filter. So we'll sort of following his path, see how he analyzes the problem. The big picture, I want to quickly talk about why we are doing this, why we are learning Kalman filter. First of all, now we are very familiar with the deterministic case of the state estimation, meaning observer design, where we don't have noise, and we know how to design observers. This is one way to design the observer. Okay, we just use the system matrices, and then we add this error term between the true output and the estimated output. So if you recall, the criteria used in designing deterministic observers, we mainly focus on how we design L such that the eigenvalue of this closed loop matrix has the desired properties. It's going to give us, for instance, the convergence of the error to 0 at the desired speed. However, now, if we have noise inside the system, these criteria has to change. For example, look at this one. If we have noise inside, it's impossible to have the error to go to 0 completely. We always have some kind of noises inside. So this criteria has to be updated. And then Kalman filter is providing a way to do this state estimation in an optimal way. And actually in the sense of, as you can imagine, these squares, which we have learned in the last lecture. So the problem statement looks like this. Now I have noise both in the state and in the output. So this is the state noise, and this is the output noise. Other things are the same. So notice that I used AK, BK, and CK. So you can see Kalman filter will work for time-varying systems as well. Okay? So to finish up the problem statement, here the noises are vectors. So W is an S-dimensional input noise. So Y can be contain multiple output as well. So V can be a vector as well. So we'll assume the initial state is unknown, because if we buy that there are errors in the states, then the last time when we stop the system, there are errors, there are noises in the system. So the initial state, when we run the experiment next time, contains some uncertainties because of this guy here. Okay? So we'll be assuming several standard assumptions. First of all, these noises are independent. The state noise and measurement noise are independent, and they are also independent from the initial state. And they are Gaussian distributed. And we'll assume that W and V are white. So be very careful next time when you are asked to design a Kalman filter. Always check whether these assumptions are satisfied or not. From time to time, you may encounter cases that the problem is not formulated in the exact way as the statement here, and you have to do extra work to make it suitable for applying a Kalman filter. Okay? Because actually, Kalman filter itself is not difficult. What's difficult is how you massage the problem into the framework of Kalman filter. Okay? So we're assuming the initial state has a mean of x0, has a covariance of x0, big X, capital X0. And these noises are zero mean, uncorrelated. And then, I will ask you a question about this. And then they are white. So if you just look at these two here, these white noises, are they stationary or not? Yes? Not quite, actually. So it's not stationary. It can be if these are constant matrices. But if it's not constant, it means, for example, they're changing the properties. Okay? So the goal of Kalman filter is what we have seen before. I have just introduced one new notation. Other than that, everything is the same. So we want to minimize, we want to estimate the state using x hat. And the information we have is these measurements from y0 to yj. Okay? So I use capital Y subscript j to indicate the measurement from 0 up to j. So this is a conditional expectation sign here. Okay? So the solution coming from least squares, if you recall, the least square solution is exactly this conditional expectation. This solution holds without any assumptions of Gaussian. Even if x, y, they are not Gaussian, this is the solution. But we'll be focusing on the Gaussian case, because the Gaussian case, this has very nice mathematical expressions. So as you have seen, k and x, I didn't say how k and j, excuse me, k and j, how k and j are related to each other. So if, imagine this, if we have j measurement, but we are estimating a future state, right? The future state, k is larger than j, then we are doing, this is called a prediction problem. We are predicting the future state using measurement from 0 to j. If, this is just notation, if k equals to j, then it's called a filtering problem. If we have more measurements, then if we have situation like this is k, and this is j, then we are using all these measurements to estimate the previous state. So it's called a smoothing problem. We'll be mostly talking about the first two problems in the lecture. So just a little bit history. That Kalman filter was invented by Rudolf Kalman. He obtained his degrees, bachelor's and master's of science degree from MIT quite a while ago, and then PhD in Columbia University. So he did his degrees in electrical engineering. But Kalman filter was first published in a mechanical engineering journal. Because the reason was that when Kalman filter was first invented, many people sort of, I guess, sort of did not quite understand the logic inside. So Kalman published that in mechanical engineering because Kalman filter was first implemented in several very big projects related to mechanical engineering, such as these NASA space shuttle, Navy submarines. So it got acceptance first from mechanical engineering, and then very soon after that, everyone in the world knows about it. So I told you before that Kalman was awarded the National Medal of Science in 2009 from President Obama. So as long as you understand this is a very important slide for today. If you understand all these equations here, then you are almost half done for understanding Kalman filter. Okay? It's a quick summary of what I had used in the last lecture. So let's go over through these four very useful facts. So suppose X is Gaussian distributed. Then now, because of that, you know Y is also Gaussian. If that happens, if we evaluate the cross covariance between X and Y, which is defined by this, then it's going to be the covariance matrix of X times A transpose. The reason for that is now if you put y equals ax plus b here. Ax plus b here. And then expected value of y equals a expected value of x plus b, because b is a constant. So now you see the b term is going to cancel, and then the remaining term is going to be ax minus a expected value of x. Now because of the transpose sign, a is going to go to the right-hand side, becomes a transpose. So this is the final result here. Now if we want to evaluate the covariance of y, it's going to be very similarly derived. It's going to be a covariance of x times a transpose. And as you can see, a appears again twice because covariance is a second order property. So if x passes through some kind of linear functions, then the covariance is going to contain the system properties. A is going to appear twice. We have talked about this before. So that's the first result. Then the second result. Now, if I have, this is sort of like we have two measurements. One is using y, and another is using y prime. Then we might be interested in knowing how these two measurements are related to each other. First of all, the cross covariance. It's going to be, now, very soon I want you to be able to write down these results without looking at the definitions. So it's going to be a covariance of x times a prime transpose. The reason for that is if you think about the definition, y is going to have some kind of structure like this. So ax is going to appear here because y equals ax. That's why a is on the left-hand side instead of a prime. And on the right-hand side, it's going to be the properties that's in the measurement y prime, because y prime is on the right-hand side. So a prime transpose is going to appear here. Any questions for this part? So reverse. If I'm evaluating cross covariance between y transpose and y, then it's going to be a transpose on the left-hand side, and then a prime on the left-hand side, and a transpose on the right-hand side. Okay? Now, things are getting more interesting. If I have both state and noise inside y, and this noise is Gaussian and independent of x, then the covariance of y is going to contain, first of all, understand that the covariance of y is going to depend on the properties of x and the property of v, the noise inside here. Then if we follow the definitions, we're going to have the covariance of x times a transpose plus this information of v. So I'll do this. I will show this once, and then I will be just using it in the remainder of the lecture. So it's kind of, you just have to write out the definition. Y equals ax plus bv. Then expected value of y equals a expected value of x. I'm assuming v, okay, I didn't assume v is 0 mean, so I have to write it down. B expected value of v, then times its own transpose, ax minus, now I'm going to shift the terms a little bit to make it look structurally nicer. Transpose. Okay? So look at the result here. The term related to x is going to give us a expected value x minus mx, x minus mx transpose times a transpose. So I'm jumping 2 steps. I'm taking out a on the left-hand side, and I'm taking out a transpose on the right-hand side. Very similarly, for the b, for the v term, I'm going to have b expected value v minus mv, v minus mv transpose, v transpose. This is exactly the result here. A times the covariance of x times A transpose plus B times the covariance of V times B transpose. Okay? So take this and absorb these equations in your mind. Right? Makes perfect sense. First of all, this derivation. Which one? Yeah, so there's a cross term between x and v. But I have said v is independent of x, so that term is going to vanish. Yeah. Right? Yeah. So this term, this v and x term, the cross product term is going to vanish because v is independent of x. Okay? All right. So the last one. Last one is now we have two measurements, but these measurements have different dynamics. Okay? One is A, B, and the other is A prime and B prime. What about the cross covariance between Y and Y prime? Then it's going to be, so here, V is Gaussian and also independent of X. So, no, here is the difference. Yeah. Now, V is dependent of X. Now, if you think about the definition here, now we're going to have a cross product term between V and X because they are not independent. This is exactly the cross product term between V and X in the result here. And the remaining result is similar to what we discussed before. So it's going to contain the covariance matrix of X and then the covariance matrix of V. Okay? So any questions for this 4 properties? If no, let me write out one example maybe. Let's see how. I'm going to write out a simple example. Y equals, let's say, 3x plus v. Y prime equals 10x plus 3v. What's the cross covariance between y and y prime? Oh, I have to tell you. Yeah, I'm assuming this. Yeah, just use use these terms, these assumptions, without giving you the explicit values. So it's going to be 3 times, in this case, it's variance because it's a scalar case, times 10. There's going to be a transpose, but the transpose is going to, doesn't matter because it's a scalar, plus 1 times xvv times 3. Then plus the cross product term between x and v. So I'm going to use 3xv times 3 plus 1 xvx times 10. Okay? So be familiar with these equations and then try to be able to write the result down without without rewriting the definitions of these cross covariance terms. Okay. Now comes the very, very essential step for deriving Kalman filter. So I'm restating the goal. It's going to minimize this square term conditioned on. Now here, typo here. Here, I'm saying I'm using all the information up to k, time k, to estimate x of k. So I'm using all the previous information. This is the filtering problem. Filtering problem. The best estimate, as we have seen before, is the conditional expectation of x given yk. Okay? Now, use this notation here. We can very easily decompose yk, all the information up to k, to be two parts. The first part is all the information up to k minus 1, and then the second part is yk. The reason I'm doing this is sort of as follows. We want to estimate x, k in the state space. Now, we have all the measurement up to time k minus 1. So imagine this is a space. This is a vector space that's spanned by this measurement y from y0 to yk minus 1. Now we have a new measurement y of k, which gives us some additional information that's beyond the information that's provided in this vector space. So it can be, it may be decomposed into two parts. One part is exactly inside this vector space, and the other part is perfectly perpendicular to this vector space. So this is exactly similar to the least square problem. Okay? So it's going to be the estimation of x is going to be the estimation of xk, first of all, using all these informations in this vector space spanned by yk minus 1, then plus the improvement using this new estimation, using this new measurement y of k. So if I want to write it down in an equation that's similar to what we learned in the last lecture, I'm going to use the notation, this vector is going to be y hat k given yk minus 1, and this is the residual yk minus 1. Okay? And this is the estimation of x hat k given this information in this subspace. Okay? So if I use the result from last lecture, I'm going to have the expectation of x. If I want to do this estimation using these two components of measurement, it's going to be the conditional expectation. This is the estimate. If I only have the previous up to yk minus 1, the previous measurement, plus the improvement if I have additionally y. So it's going to be the expectation of x tilde k given conditioned on yk minus 1. This, as you can see, is this vector here. Then another condition on y tilde k given yk minus 1. If you understand this equation, you are almost done with deriving Kalman filter. So any questions for this part? Mm-hmm. This one doesn't add information because this is inside this vector space. No, because no, it's not that case. Because if it's in this vector space, then it can be expressed as a linear combination of the basis vectors in this vector space. Yeah. Yeah, coefficients can be different. It will not, unfortunately. because it's just similar to this case. So imagine you have a matrix. The columns, let's say 1, 0, 0, 1, 1, 1. Then maybe 1, 2. The first two vectors already spans the 2D space, right? Now, these additional vectors can all be expressed as linear combinations of these vectors. So it will not provide additional. This is providing the minimum required information to let me express any vector in a 2D space, right? Still will not, unfortunately. Mm. The state of the system will be the same. The estimation of the system, yeah, the optimal estimation of the system will use all the information I can obtain. Mm. Yeah. Mm. So everyone sees this equation here? Understand it? Then, great. I just have, this is how this equality comes from over here. Okay? So as you can see, we already have very heavy notations here. So it's very useful to introduce some new notations to simplify the writing here. The notations we're going to be using are as follows. So first of all, this term is the estimation of x. So it's x hat. We want to estimate k, and the information we have is up to k minus 1. So this is the notation here. X hat k given k minus 1 is for the first term. And then similarly, for this term, we are estimating x using all the information up to k. So this is how this notation comes from. So just some additional, to distinguish these two, when we are writing out, they are both estimations, but one of them is using more information. Is using the information up to time k, so it's called a posteriori estimation. And because of this notation here, we're going to have something similar, but different name. It's called a priori estimation. So it's not using the most up-to-date measurement y here. Okay? And because we have these two estimations, so we got to be able to express the variance, the covariance error, covariance of the estimation error. So for the first term, a priori estimation, we express the covariance, the estimation error covariance as mk. So as you can see from the definition, it's the covariance of the residual error of xk given yk minus 1. And similarly, we use zk to say is the a posteriori covariance of the estimation error. Okay, so using these notations, we can simplify the equation here greatly. So look at this result here. If I say this is already, we know, the a priori estimation. So we only need to worry about this additional term here. So can someone tell me what kind of information do I need to do this conditional estimation, conditional expectation? Cross covariance between x tilde and y tilde, and then covariance of y tilde, all these informations. All right. So this is using the least square property 3, number 1 equation over there. So we have just talked about that we need these, the cross covariance and the covariance matrices. So now we are immediately going to use the very useful facts. of the four properties I mentioned earlier. I know yk equals cxk plus vk. Okay? Then I'll be able to know. So I wanted to obtain this guy. So what will be, so to be able to get this, as you can see, we need yk minus y hat k. I'm going to start to use the notations I introduced in the last slide. I'm going to need this. So I'm going to need this guy. What will be y hat k given k minus 1 here from the definition of y? How do we do this step? Yeah, it's exactly. So what about this term? If I have only information of y0 to yk minus 1, how will I be able to estimate v of k? It's mean value, right? So so the assumption is vk has nothing to do with these. The assumption is vk is totally white noise. So we don't know. We will not be able to provide any better estimation of v using these measurement up to k minus 1, because this is happening. Looking at this is happening in the future. It's at time k. So we won't be able to improve. We won't be able to have a good estimation of this except its mean values, right? But the mean value is 0, so this is just 0. It's the assumption at the beginning. So now you see y tilde k given k minus 1 is going to be axk plus vk minus cx hat k given k minus 1. Then 0. I won't write 0 again. So it's going to, no, I made a typo. It's going to be C. Sorry. Okay? So now, look at this guy. Someone can directly tell me what is y tilde k, yk minus 1. What about this one? Can someone immediately tell me what is this? Using some right. So that's not finished though. Be careful. Yeah. So it's going to be C. You see here. So first of all, think about this. Understand this. The statistic property of y is going to y tilde is going to absolutely contain information of x and also v. So we will have at least 2 terms. Keep that in mind at the beginning. So then later, look at this too. This quantity and this quantity here. So I'm going to have C, the information of x, given k minus 1. And then there's going to be a C transpose sign. Then there's going to be another term that's telling us the information of v, right? It's the covariance of v itself. I think I'm assuming in the reader, I'm using this as the covariance of v. Yeah, I'm using that as the covariance of v. It's okay? Everyone sees this? If you see this, then let's do one more exercise to let you get familiar with the properties. What is the cross covariance between x tilde and y tilde? Give you a little bit more hint. It's going to be cx tilde k minus 1 plus vk. It's very close, but think about it more. It's almost the answer. Anyone has another guess? So let us do one more step. So write down the definition a little bit. Minus the mean of x k minus 1 times y transpose k minus 1 minus the mean of itself. Transpose. Now, what is the result we're looking at? So you see here, x is on the right, is on the left-hand side. So it's going to be x tilde, k minus 1, x tilde k minus 1, C transpose. Then anything else? Because v is uncorrelated with x, so there's no more term. Okay? So get familiar with these notations. So here I'm using the constant case. C is constant, but it doesn't matter if C is a time-varying matrix. And the case for the time-varying matrix is it's used here. So if it's time-varying, we're going to have, oh, the result is here. Result is here. So I just used recall this definition. This is x tilde k minus 1, x tilde k minus 1. Okay? So that's exactly what we derived a moment ago. Okay? So with these guys, we'll be able to write this without problem. And the answer is going to be how do I put it? The answer for this guy is going to be on this slide. The answer is this. Okay? This is the cross covariance between x tilde and y tilde, and this is the inverse of the covariance of y tilde. And then here, we have to know the mean of y tilde k given k minus 1. And then we have to know the mean of this term. But these are relatively much more easier to obtain than the two central quantities here. Okay? So the mean, it's kind of very natural to understand the mean is going to be 0. Because first of all, our estimation we discussed last time from the least square properties, the estimation is unbiased from last time. So if you take the mean of this guy, it's going to be 0. And because the mean of x tilde is 0, now look at the definition of y tilde. If this is 0 mean, this is 0 mean, then this is absolutely 0 mean. So this is also 0. Okay? So using the formal, now using the notations, this is the final result. The equation looks long, but you take a moment to look at this. You see, it makes perfect sense. First of all, there's a big inverse matrix here. And this inverse matrix is the covariance arrow of y tilde. Now, y tilde is going to contain information of x tilde and v. So there's going to be something about v here. And then this is something about x. We have talked about that. M of x, mk is covariance of x tilde k, k minus 1. Right? And on this side, I'm going to have the cross covariance between x tilde and y tilde. So it's definitely going to contain information of x tilde. And because y is happening on the right, here, I'm going to have C transpose. Okay? So things make intuitive sense. And finally, this yk minus y hat k is this y tilde term over here. Okay? So now, we have actually essentially derived the one of the most important equations in Kalman filter is this guy. So now we have, if I want to estimate xk given yk, all the information up to yk, then it's going to be this guy. So in the notation, it's going to be x hat k given k equals x hat k minus 1. And then this term is going to be mk C transpose. Okay, I don't have much space, so I will write down the case for constant matrices ABC, but it doesn't matter for if C is time varying. I'll write VK inverse, and then finally it's y tilde k given k minus 1. Okay? So the result is this. And very similarly, you can see the structure looks very much like the case for an observer. Recall, we have the observer system matrix at the beginning of the lecture. The observer equation looks like this. Okay? Compare this guy with this guy. Then you see this is sort of the estimate x hat k plus 1. The notation is shifted by one index. Oh. Okay. So the first term is exactly this term here, ax hat k plus buk. This is estimating using all the information up to k. You see, all the information up to k to estimate x hat k plus 1. And then this term is exactly looks like this term. This is the arrow term, and this is the arrow term here. And L, now the difference is L is replaced with a matrix here, f of k, which now depends on the statistic properties of the noises in the system. Okay? So Kalman filter, the message from here is Kalman filter is a special type of observer. It's optimal in the sense about the statistic, using the statistic properties of the noises in the system. Yeah, it's optimal in the sense that the covariance of the estimation error is minimized. It's actually this. Yeah, but this is sort of a nice question. What is actually happening is so for the filtering case is this. Oh, x should be x. The variance of this is minimized, right? We're minimizing this, okay? And then I mentioned covariance matrix because this guy is the trace of the covariance matrix. This is something I discussed last time. Yeah, so it's in the sense, that sense. So this is in the sense of what's the optimal goal we are arriving here. Okay? So we can write it a little bit more compact. So using this, break it down into two equations. So in practice, we can compute this gain offline first. So we can compute these gains because these gains, look at them, they depend on, no, I have to introduce another equation first. So I'll explain how these gains are computed in a while in practice. Okay, so what's remaining for us to be able to implement this Kalman filter? Just by looking at this equation here. What are the terms that we don't currently know how to get yet? Which one? Yes. So you see, these we know, but this guy, I haven't talked about how to do this. So how to do the variance update? It's actually variance or covariance. More accurate should be covariance. How to update, exactly obtain the update equation for m of k, okay? This is going to be using, again, property 3 of least square update estimation. So look at this. First of all, this first equality is using nothing but breaking yk down to two parts. The first part using the previous measurement up to k minus 1, and the second part is yk. Then I'm going to do exactly the same thing as the second equation for property 3 in the least squares. So I am going to, first of all, try my best to update using all the information up to k minus 1. And then I'm going to improve my estimate using this additional information given by yk. Okay? So this is exactly property 3 of least square estimation. Okay? So let's see what are the things here. This term, as you can see, using the notations we have been using, this is m of k. All right? And this term I want to express is z of k. In the notation, it's called z of k. Okay? So for these additional 3 terms, we have already obtained it in a few slides ahead. So what is the first term? If k is a c plus vk. The first term here. This is sort of as a review and exercise. So I want to obtain the cross covariance between this guy and this guy. Write down the definition and tell me the answer. So it's going to be the covariance. So you know, why don't you just tell me? I don't understand. You're afraid of making mistakes? Is this guy. So because this guy, we have defined this as m of k. All right? What about the second term? Yeah, so now this time I will write down the full notation using m. What about the last term? Yeah, the last term is actually easier to obtain. Either you can look at this guy, or you can say this has to be the transpose of this. So it's a transpose of this. So it's CMK. All right? So you see, you already understand how this looks like. You're just sort of not willing to tell me somehow, right? So z of k is updated by m of k minus m of k times c transpose k, and then this big inverse matrix, and then lastly cm of k. Okay? So it's just one slide more, you will fully understand the equation. So notice that I have both z and m here, but in the implementation we are using only m. So we have to figure out the connection between z and m, how they are dependent on each other. So how z and m are connected. Let's see. This guy is also pretty easy to do. So starting from here, this is the definition of k, x of k. It's the system matrix is AB, and then the noise inside this. This is the system state matrix. Okay. So from here, you see, we have talked about this concept. If I want to estimate x of k, given the information up to k minus 1, then what I can do is I can filter this estimation at k minus 1 using this through this system matrix. But I don't know anything about from this is, if I write it completely, I should say plus BW k minus 1, but I don't have space for k minus 1, so I will write it like this. The complete expression should be k minus 1 given k minus 1. All right? I want you to understand, we won't be able to do an estimate, should be had. We won't be able to estimate the state noise because, think about it, yk minus 1, this is the last measurement we can get. It equals c x k minus 1 plus vk minus 1. Okay? And then this, yeah, it's hard to say, write completely because all the notations. So xk minus 1 equals a xk minus 2 plus buk minus 2 plus buk minus 2 plus, this is the key here, plus bw. What is the w, index for w here? K minus 2, right? So you see, xk k minus 1 depends only on wk minus 2. It doesn't depend on wk minus 1, right? So then, in a sense, if I only know yk minus 1, then I won't be able to write out any information with respect to k minus 1 because this guy only tells us wk minus 2, k minus 2. So you see, that's why we won't be able to provide a good estimate of w given only yk minus 1. The best way we can do is take the mean, which is 0. So that's why there's no additional term here. Okay? Now, take the subtraction. X tilde is xk minus xk, x hat, k given k minus 1. So it's going to be this system matrix, this guy minus this guy, x minus this guy, which is x tilde. And you see, the control input, the deterministic information is cancelled. It's always the case. The deterministic equation wouldn't be a trouble. The trouble is the noise term. The noise term is going to remain here. Okay? Now, using this, can you tell me what's the relationship between zk and mk? Let's see. I think I'm using zk minus 1 and mk. Let me check. Yeah. What's the relationship between these two by looking at this equation here? This plus BW K minus, yeah, oh, I forgot the K minus 1. Then what? This is one very promising solution, but unfortunately it contains errors. Huh? If you can correct the answer within 3 seconds, I can give you hints for the next homework. Yeah. So because these are second order properties, so the system matrices has to appear twice. So someone proposed this new expression. Is this correct or not? Anyone think it's incorrect? So you think it's correct? It is indeed correct. So this is how M and Z are related, okay? And as you can guess, we have to somehow initialize the estimation things. So the estimation, how we can estimate x at time 0 if we don't have any information at all, then the best thing we can do is we use the covariance of x. So this is how the equations are initialized. Okay? So that's the derivation of Kalman filter. As you see, it's just repeatedly using the properties of these squares. And by the way, this derivation here is slightly different from the one in the cost reader, which is using induction to prove it. But the conclusions are exactly the same. So these are the central equations for Kalman filter update. So yeah, let's take a moment to read these. So the estimation of x, given all the information up to k, is we are improving the estimation given all the information of k minus 1 with the new measurement yk. Okay, this is how the first equation looks like. And then if I want to estimate, if I want to obtain this quantity here, then I don't have much information up to k. Then the best way I can do is I can filter this process. So this is for x k equals ax k minus 1 plus, again, I'm using the constant matrices, but it doesn't matter. It holds also for the time varying matrices. This is k minus 1. Okay? So the best way I can do, if I have x hat k minus 1, given k minus 1, is to filter it through the system dynamics without the noise term, because I don't have the noise term. And then we have explained that Kalman filter is an observer. It's optimal in the sense that the gain, update gain, is specially computed depending on the properties of the noise terms. Okay? And how these M matrices are computed are just what we have discussed in the last 2 slides. M is dependent on zk minus 1, but zk minus 1 has some kind of regression term. And that's how Kalman filter equation, a full set of Kalman filter equation looks like. So depending on the preference, we sometimes use this kind of system matrices. So in other occasions, it might be preferred that we use this system dynamics, which is also fine, totally fine as well. It's just a shifting a time index. So if we say we shift one time index, then it looks like everything is shifted by one time index, and this is the formula in the reader. So everything is the same. It's just the shifting of the time index. Okay. So you might see that actually we only need to use matrix M in the state update. We actually are not using Z. So we can combine these 2 equations and eliminate Z for implementation. And if we do that, look at what will happen. I have to substitute M of k plus 1 into here. Okay? Substitute this here, substitute this here, and here, and here. Okay? Then you can see the equation, the result of the equation looks like this. It's actually a Riccati equation. Okay? For the moment, don't worry too much about this Riccati equation. We will explain a little bit more about this. It's just a way to compute the matrix M in the Kalman filter. Okay. Look at this term. Now I'm going to talk about how this is implemented. So to implement this Kalman filter, I'm going to need the gain F matrix. And then to do that, I'm going to need the matrix M, which comes from this Riccati equation. Now, look at this Riccati equation very carefully. We have no problem knowing the system matrices. All right? A, B, where is B? But it doesn't contain B. We have no problem knowing A, B, W, and C. And if we know the statistic information of the, this is coming from the output noise, and this is coming from the state noise. If we know these, then we'll be able to iteratively compute this M matrix, right? If we start at time k equals to 0, then we can compute M1, and then we can, after that, we can compute M2, M3. And we know M0 equals to X0, which is the initial variance of X. Okay? So you see, we can compute these. All these terms doesn't explicitly depend on X of K. So all these terms we can compute offline, meaning we can obtain the matrices M and F offline first. When we implement, we just put the matrices here and run it online. Okay? So, M. Mm-hmm. Yeah, that is also fine. Yeah, it's just to do that, you have to compute like two steps, but this is just one step. Yeah, it's totally fine. So the message I wanted to say is that the matrices Fk, Mk, and Zk can be obtained offline first. When you implement, just implement these matrices, store these matrices in the computer and run it online. So there are a couple of concepts I want you to see. Is that, first of all, as you can see, Kalman filter is linear. I didn't use any nonlinear functions in Kalman filter. And Kalman filter is optimal for Gaussian. So if, let's say, this means, the first statement means for Gaussian noise case, then it won't help if I use like second order or any type of nonlinear estimation schemes. Kalman filter is, this linear filter is sufficient to obtain the optimal solution for Gaussian, all right? So more advanced nonlinear estimation won't improve the results here. The only possible way to improve it is the case when the noise are not Gaussian, okay? So yeah, this is something I mentioned before. Kalman filter works for time-varying systems. And if you want to write down the block diagram of the Kalman filter, it looks like this. So the measurement is compared with this estimation, yk minus ck times this x hat k minus k given k minus 1. Okay? And this arrow, this is, I forgot which notation I used, but let's say this is the arrow term. And this arrow term, you see, is used to train this estimation, is to improve this arrow term. This arrow information at time k is used to improve the state estimate by filtering through this Kalman filter gain matrix. And the other parts are just the system matrix inside. Okay? So all these previous discussions holds for time-varying systems. Now we're going to take a closer look for the case of time-invariant systems. And over there, several properties are pretty nice. So if the system matrices are constant, and the noise term now, this is why I asked at the beginning whether the noise terms are stationary or not. If the noise terms are stationary, okay, meaning they are statistic, the covariance doesn't depend on time, then the Kalman filter becomes all these constant matrices. So C, A, B, these are become constant matrices inside. Then the most important message comes from here. We have a Riccardi equation that looks like this. Recall, we learned in LQ problem, discrete time LQ problem. There's a Riccardi equation over there. Under what condition does the Riccardi equation converge to a constant steady state matrix? The controllability condition, right? So you see, because it's also a Riccardi equation, so the convergence is exactly the same. We don't need to prove anything. We can simply say, state the conditions for convergence of the Riccardi equation. So the result is like this. I will tell you the result first, and then I will explain why they are like this. The result is AC has to be observable. The convergence is this case. Let's explain the full statement first, and then I will tell detailedly which one is for which. AC has to be observable or detectable, and then A, BW has to be controllable. But because BW is the matrix for the noise term, so it may sound more intuitive to say that it's disturbable, meaning the noise can disturb the system in the sense. But it's saying this system, this pair A, B, W, the controllability matrix coming from here has to be full rank. That's the mathematical expression. Okay? So then the Kalman filter, the Riccardi equation, is going to converge to the steady state value. And then this gives us the benefit of we can now use constant matrices in the Kalman filter because M is a constant, converges to a constant. So f of s is going to converge to a constant. So this is even further simplifying the computation in the sense that we're just running a constant gain observer in the actual implementation. Okay? So now let's explain which case, which statement here are for the convergence of the Riccardi equation. So if you recall the LQ problem, this is the discrete time LQ, Riccardi equation in discrete time LQ. And this is the Riccardi equation in Kalman filter. Okay? They look very similar, very, very similar, except some minor differences in the sense that this is A transpose. The A transpose, the A seems to become A transpose, and then in all these update equations over here. All right? So when Kalman discovered this, he found out this kind of duality between LQ and Kalman filter. So if you compare the Riccardi equations look like this, the connections are like if in the discrete time LQ problem we have A matrix, then in over here becomes A transpose, and the B matrix becomes C transpose. This B is C transpose, and then this Q is this BW transpose term, and this P is M. So you all have seen that the convergence condition for the Riccardi equation is that AB is controllable. All right? So what about the convergence condition for this Riccardi equation? By noticing this duality. You're going too fast. It's going to be A transpose. So A transpose, then C transpose has to be controllable, right? So this is the minor thing I want you to notice is that A transpose, C transpose controllable is the same saying AC observable. Okay? So to show this, you just construct the controllability matrix of this guy, which is going to be C transpose, A transpose, C transpose, A transpose, square C transpose, then going all the way to as long as the system dimension looks like. So this guy has to be full rank. But you see, this matrix is nothing but this. It's the transpose of CA square, right? It's exactly the transpose of this guy. If this is full rank, then it's saying this is full rank. If this is full rank, it's saying AC is observable, right? Any questions for this part? So similarly, if I ask you, what about A transpose, BW transpose being observable? Then it's equivalent to say A BW is controllable. Okay? So keep this in mind. Then we can come back here. Okay? So someone tell me, which of the conditions here are for the convergence of the Riccati equation? So it's observable. So this is the difference. So it's not the controllable condition that makes the Kalman filter converge. The Riccati equation converge. It's this guy. It's the observability condition makes the Kalman filter converge. Okay? All right. So we have explained that this guy, here, the observability condition is for convergence of ARE. And the other condition, the controllability condition, is for the M of S to converge to a positive definite solution, and then for the Kalman filter to be stable, asymptotically stable. Okay? Mm-hmm. Let me take back the slides. This? Yeah. Yeah, so that's the difference here. Yeah, it's a good question. So in discrete time LQ, we are going backwards. We're going from k plus 1 to k. And in this case, we're going forward from k to k plus 1. But mathematically, when computing this, whether going backwards or forwards doesn't change the convergence. Because, yeah, right? Yeah, so it doesn't matter. The convergence is still the same. Okay? So now comes the sort of the nice idea of the Kalman filter. So in discrete time LQ, you learned that the steady state LQ problem gives a asymptotically stable closed-loop system. That's the benefit of LQ, right? So because of the duality between LQ and Kalman filter, then we have exactly the same conclusion that the Kalman filter loop is always stable if we have the controllability and observability assumptions. Okay? So just a little bit more, this is the main message, that the Kalman filter is asymptotically stable. This is just the additional information telling us which matrix are stable over here. So in the LQ problem, we have this, because we have xk plus 1 equals axk plus buk, and uk is the control law, state feedback control law. So in LQ problem, it looks like this. It's A minus BK. And in Kalman filter, the system, sort of the A matrix, that's equivalent to this guy. It's going to be coming from how the previous state estimate is going to connect to the current state estimate. So this is, if you do the algebra from here, from here and substitute the Kalman filter equations, then this is the closed loop A matrix for the Kalman filter. So the conclusion is that this matrix, the eigenvalues of this matrix is always inside the unit circle, all right? So let me ask you one question. Does Kalman filter apply to unstable plants? Think about it. That's one way to think about it. But think about it, I'm only estimating the states, but the unstable plant can be stabilized by a controller first. The state, unstable plant doesn't mean the state will blow up, right? So the answer to that is Kalman filter applies to unstable plants as well. And that's actually the power of Kalman filter, right? Yeah, the states, first of all, if you're estimating the states shouldn't blow up at the beginning to start with, right? So that's, we almost, I think we finished talking about. So as a summarize, so I will summarize today's lectures by concluding on the benefits of Kalman filter. Okay, so we talked about under observability assumptions, we can use a constant update matrix to update the Kalman filter. And then if we have the controllability assumptions, the Kalman filter dynamics is asymptotically stable. And the covariance matrix is going to be positive definite. So that's the benefit, very similar to discrete time LQ problem. LQ problem says that the closed loop system is always stable in the LQ problem. And we have the fantastic margins, gain margin, phase margin in that case. Okay, so we're going to talk about the additional properties of Kalman filter in the next lecture. All right? Okay, see you next week.